So we're now going to talk about how do we solve differential equations like x times y double prime plus 5x squared times y prime plus 3y times x to the fourth equals 0, noticing that the coefficients of the derivative terms are not constant as they've been in the past. We want to talk about how do we solve this. You can use different methods, but one method we're going to talk about is using series solutions to do that. And what we mean by series solution is we're going to think about the solution to this is of the form that y is equal to the summation n equals 0 to infinity of Cn x to the n. And so that's what we're doing. And our whole job with doing this is to figure out what is that C sub n, what are those different terms, and what do they equal? And then we can get these power series solutions. So this is what we're going to look at. To help us with this, it helps to have a little bit of a review of power series. If we do have, by the way, if we have f of x equals the summation n equals 0 to infinity of Cn x to the n, then we can in fact find f prime and the integral of f of x. So as a reminder from series information, you were able to find the derivative and the integral of a power series. A couple things about power series is that, remember the way this works is that this means, let me give myself a little bit of space here. Is the way a power series works is that this is equal to C0, x to the 0, plus C1, x to the 1, plus C2, x squared, plus, and you just keep going on. One term we're going to have is we can call it Ci minus 1. X to the I minus 1. And then you just keep going with that forever and ever and ever. And it just keeps adding up and keeps going forever in this process. There are many different functions that have power series representation. E to the x can be written as a power series. It is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and it keeps going forever and ever and ever. Notice in this case, the C0, C1 is 1 over 1 factorial, 1 over 2 factorial, and so forth. So you can see kind of that pattern that's in it. In fact, if we look at this, that pattern would be the summation of 1 over n factorial x to the n, where n goes from 0 to infinity. So we do see we actually have a nice process behind here. Again, other functions that can be done this way, a sine of x is 1 minus 1 over minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, and it just keeps going. This it's called an alternating series because we alternate the signs, plus, minus, plus, minus. And again, you can try to figure out how to write this in its summation notation if you want to. The cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus. And again, it's an alternating series and it just keeps going forever and ever. And you can figure out how to write this in that format. All of these and more that we're not going to write them all down, but there's more that you can look at. These are all converge on the absolute value of x being less than infinity. So in other words, these converge for all x. They don't all converge for all x. So sometimes we need to look at some other ways of looking at it. There are others that we can look at. The textbook has some that's also available online. The other thing to remember is that you can add, subtract, multiply, and divide power series. So we can do different things with these power series. F is called analytic if F can actually be represented as a power series. So this is one of the things we work out with power series is if we can actually put it in this format and analyze it this way and write it as a power series, then we call it analytic. There are many functions that are not analytic. And we like to work with the ones that are, but there are other ones that are not. The gamma function is a good example of one that is not analytic. We can, and actually I'm going to go back just for a moment. I'm going to talk about how do we actually find that where it does converge. If it doesn't converge in all places, how do we find that interval of convergence? So that interval of convergence is where it converges. So the interval of convergence is the interval where the interval that it converges on. So the interval, the series converges, the power series converges. And we find that radius of convergence by looking at the fact that the summation n equals 0 to infinity of Cn x to the n, the interval of convergence, and actually I'm going to make this one just a little bit different here. We're going to actually call this Cn x minus a to the n. And this converges on the interval if the absolute value of x minus a is less than r, and then r is known as the radius. And there's different ways to find out what that is and figure out different ideas. I'm not going to review all of the ideas behind power series convergence and so forth, but I wanted you to know a little bit about it. We can actually do an example of here where we're trying to find an interval of convergence. So find the interval of convergence. And the radius of convergence. Of, let's take as an example, the summation n equals 0 to infinity of 1 over n squared x to the n. So we want to find this radius of convergence. One way to do this is actually to look at the radius, the ratio test. So what we're going to do is we're going to actually take the limit as n goes to infinity of, let's say, a to the n plus 1 over a to the n. That's the ratio test. So we take the limit as n goes to infinity of x to the n plus 1 over n plus 1 squared over top of x to the n over n squared. So we want to find out what this ratio is, figure out what this is. I'm simplifying a little bit here. We can see that we have the limit as n goes to infinity because we haven't taken the limit yet. X to the n plus 1 over x to the n is just x. Yeah, it's just x, sorry. And then n plus 1 squared over n squared, well, we don't know what that is yet, so we just write it as n squared over n plus 1 squared, just simplifying this to be not a complex fraction. All right, and so now we have to figure out what this is. And so looking at this, the x is not involved in this limit, so we can pull the x out. It is the absolute value still, so we'll pull the absolute value of x out. Limit as n goes to infinity of n squared over n plus 1 squared. We want to find out what that is. So one of the things you could do is multiply out the denominator. So let's do that. Don't lose your absolute value of x out here still. And so we have n squared over n squared plus 2n plus 1. And then we can take the limit as n goes to infinity. We can use L'Hopital's rule because this is infinity over infinity. And L'Hopital's rule would be we do 2n over 2n plus 2. Do the L'Hopital's rule again, you get 2 over 2, which is 1. So we end up with the absolute value of x. And we know that this is going to be less than 1 because this limit is 1. So we know that this is going to actually be less than 1. So we have that information. So therefore, our interval, we do need to find out whether or not we converge at the endpoints. So this is just seeing less than 1. So let's look at x equal to 1. If x equals 1, then the summation of n equals 0 to infinity of 1 over n squared, 1 to the n, because x is 1. That is equal to the summation n equals 0 to infinity of 1 over n squared. Well, that's a p-series, and we know that that converges. We're going to look at x equals -1, the other end of my endpoint. N equals 0 to infinity of 1 over n squared, -1 to the n. And so that's equal to the summation n equals 0 to infinity of -1 to the n over n squared. Well, that converges absolutely because it's an alternating series. This converges absolutely. And so we now know that our radius, we were saying we're less than 1, so our radius is 1. And our interval, we now know the endpoints are included, so we can go from -1 to 1. And there's our radius. Okay. So now we want to be able to take some derivatives and do some different things with it. And one of the things we have to do, which we didn't spend a lot of time with in the past, is we need to be able to actually shift the power series. So we want to be able to actually shift these summations so that first off, both summations start at the same place. This summation, the summation n equals 2 to infinity of n plus 1 times n minus 1 times n times cn to the x to the n minus 2, plus the summation n equals 0 to infinity of cn x to the n. We want these both to start at the same place. They start at, one starts at 2 and one starts at 0. So we have to figure out how to make that happen. So one of the things I noticed is that we could actually replace n with n plus 2. And the reason I'm doing that is because I noticed that if n is equal to n plus 2, then we're going to put an n plus 2 in down here. N plus 2 equals 2 means n equals 0. So we would now start this at 0. So this would mean we now would do n plus 2 equals 2 to infinity, n plus 2 plus 1, n plus 2 minus 1, n plus 2, cn plus 2, x to the n plus 2 minus 2. We aren't doing anything with the other one. So this one is still cn x to the n, starting at n equals 0. So I don't have to change both. I only have to change one. I just need to shift one of these. When I do this, I happen to notice that n plus 2 equals 2 means that n equals 0 to infinity. So we now know they start at the same place. This would be n plus 3. We'd have n plus 1, n plus 2, c sub n plus 2, and then x to the n. And then the summation n equals 0 to infinity of cn x to the n. Well, now I notice they both start with the same place. I also happen to notice they both have an x to the n in them. And that actually was the more important thing, is that I want them both to have the same x. If they don't start at the same place, we could deal with that, but I wanted them both to be x to the n. Because now what I can do is take them under the same summation. They both start at the same place. We have n plus 3 times n plus 1 times n plus 2 times c n plus 2, then times x to the n, but then we also have this plus c sub n times x to the n, and so we know we can pull the x to the n out. And so this is actually this n plus 3, n plus 1 times n plus 2 times c n plus 2 plus c sub n. This is your coefficients of your x to the n, of your power series. This is what your coefficients are equal to. And so it allows us to get that information and get us to that state. So we want to actually express as a single power series of x to the n, the summation n equals 1 to infinity of Cn x to the n plus Cn x to the n minus 1 plus 3 times the summation n equals 0 to infinity of Cn x to the n plus 2. So we want to actually make these in to where they're started at the exact same, well, we don't care about starting necessarily right now. We care more about the fact that we want them both to be x to the n. And they're not. They're both, one is x to the n minus 1 and one is x to the n plus 2. So one of the things I'm going to look at is the fact that in the first one, I'm going to say that n is actually equal to n minus 1. So that's what I want to think about doing, is making it that way, because then I'm replacing the n with n minus 1. In this other one, I want it to be n plus 2, so I'm going to replace n with n. I'm going to replace n plus 2 with n. So kind of thinking of it this way, this is what you're looking at here. And so what we end up having here, and this actually, now I look at it, won't actually work, because if I put that in there, if we're replacing n with n minus 1, then I get an n minus 2. So think of it replacing the n with n minus 1. I can't do it that way, but if I replaced n with n plus 1, then notice that n plus 1 minus 1, which would give me an n here. This one here, I have an n plus 2, but I want to get rid of the plus 2. I want that plus 2 to go away. So if I actually replaced n with n minus 2, then it would go away. So that's actually what we're going to do here. So everywhere you see an n, you're going to put in an n plus 1. So I'm going to have n plus 1 equals 1 to infinity. Then I'm going to have n plus 1, instead of that n there, I'm going to have an n plus 1. C sub, instead of being just n, it's going to be c sub n plus 1. X to the, I'm replacing that n with n plus 1. And then I have that minus 1 there. The next one, the summation 3 plus 3, and then we're going to start, instead of being n equals 0 to infinity, we're going to replace that n with n minus 2. Then instead of having a c sub n, we're going to replace that c sub n, we're going to put it as n plus minus 2. And then we're going to have x, instead of just being n plus 2, it's going to be n minus 2 plus 2. All right. So now let's just simplify things a little bit here, see what we have. This is going to be the summation. N equals, since this was plus 1, you're going to subtract 1 from both sides. This one now started n equals 0 to infinity. You're going to have n plus 1, c sub n plus 1, x to the n, because n plus 1 minus 1 is 1, as n, sorry, plus 3. Now this one's going to start at n, it was n minus 2 equals 0, so solving for n, you get n equals 2 to infinity. C sub n minus 2, x to the n, because n minus 2 plus 2 is just x to the n. I'd like to put these together. One of the things I noticed is that the summations don't start at the same place. I can't shift them again, because if I shift them again, I won't have x to the n. So I want to leave these with x to the n's. But I want to think about the fact of what does this x equals n equals 0 to infinity means? It means that I'm going to let n equal 0. So 0 plus 1 times c to the 0 plus 1, x to the 0. I then let x n equal 1. So now n goes up to 1. So I have 1 plus 1, c 1 plus 1, x to the 1. Plus now n is going to be 2. So I could keep writing this, or I could just realize that now I can actually say I've got n equals 2 to infinity of n plus 1, c to the n plus 1, x to the n. Then I have this plus this 3. I'm going to take the 3 inside. N equals 2 to infinity of 3cn minus 2 x to the n. And now I notice these two summations start at the exact same place. So they're both of them starting at x squared and onward. So you can actually think about putting them together and factoring out. So now what I have here is I have 1 times c sub 1 times x is 0, which is 1, plus 2 times c sub 2, x, plus the summation n equals 2 to infinity of n plus 1 c sub n plus 2, sorry, n plus 1. Didn't read my thing very carefully. C sub n plus 1, x to the n, but we're going to pull it, we have another term, plus 3 c sub n minus 2. Both of them have an x to the n, so we can factor the x to the n out. And this again, this n plus 1 times c sub n plus 1 plus 3 c sub n minus 2. Those are the coefficients of my power series. Now what I'm going to do is just show you a simple example of how we can actually solve with power series. So we'll do a quick example of that. So this one I'd like to solve 4y prime plus y equals 0. Again, this is actually one that has constant coefficients. So I don't need to do this with power series, but I want to use this to show you how to do with power series. So y is going to equal the summation n equals 0 to infinity of c sub n x to the n. So that's what the power series notation is for power series. So we're going to always use power series here. I notice this is a solution. So that means I can substitute it in. But if I want to substitute it in here, I also need to know what y prime is. So now we need to remember how we take the derivative of power series. Or just as a derivative with anything, you bring the power down, subtract 1 from the power. So this would be n c sub n x to the n minus 1, the summation. But instead of starting at n equals 0, the summation actually starts at n equals 1. Because if you think about writing this out, you can have c0 x to the 0 plus c1 x to the 1. If I take the derivative of that, the first term is 0, it goes away. So the very first term we start with is the first term, n equals 1 instead of n equals 0. So that's why you need to do that, is make that separation. So now we're going to go ahead and substitute it in. We have 4y prime plus y equals 0. We're going to substitute it in. We have 4 times the summation n equals 1 to infinity of n c sub n x to the n minus 1. Plus the summation n equals 0 to infinity of c sub n x to the n equals 0. So this is where we have to think about that shifting the summations. We actually want to make both these have an x to the n. So the second one is already x to the n. So we don't have to do anything to that one. But this other one, we do want this to be x to the n. So what I want to think about is, what am I going to let n equal? Well, again, you want this n minus 1 become an n. So that must mean you're going to let n equal n plus 1. So you have an n plus 1 minus 1, which is just n. So in this one, everywhere I see an n, I'm going to replace it with an n plus 1. So we have 4, the summation. And so now if I'm placing that in, we have n plus 1 equals 1 to infinity. Then we're going to have n plus 1. And then we're going to have c sub n plus 1. And then we're going to have x to the n plus 1 minus 1. And then we have plus the summation n equals 0 to infinity, c sub n x to the n equals 0. All right. So now we can see how we can simplify this a bit. We have 4 times the summation n equals, well, n plus 1 equals 1 means solving for n, you get n equals 0 to infinity. N plus 1, c sub n plus 1, x to the n, plus the summation n equals 0 to infinity of c sub n x to the n equals 0. And I'm out of time. Stop sharing. Stop recording.